Well, good evening, and thank you very much for coming, and a particular welcome to those of you who are here for the first time. And also welcome to the launch of Combinatorics, Ancient and Modern, our recent book on the history of combinatorics, and we believe actually the first full-length book on the subject. So the purpose of today is to tell you what the subject is all about and how it arose historically, and I'm going to include many fascinating examples from the book. So first, what is combinatorics? Well, although the term means different things to different people, roughly speaking, it's the branch of mathematics that's concerned with selecting, arranging, and listing or counting collections of objects, usually finite collections of objects. So included here are permutations and combinations of the objects in a set. There are recreational problems from graph theory, such as the Königsberg Bridges problem, which you'll see later on, and the four-color problem. There are magic squares and Latin squares, including the sudoku puzzles that thousands try to solve on their way to work, unaware that they're doing combinatorics. So the chapters of the book were written by distinguished combinatorialists and historians of mathematics from around the world. In the ancient half of the book, we present the multicultural origins of the subject, and then following a brilliant and wide-ranging overview by the distinguished American computer scientist Donald Knuth, who incidentally a few years ago attended some Gresham lectures, we feature the early combinatorial concerns of people from China, from India, the Islamic world, and the Jewish scholarly community, before we move forward to look at combinatorics in Renaissance Europe. By way of contrast, the modern part of the talk is arranged thematically rather than chronologically, and it includes such areas as graph theory, block designs, and Latin squares. And you'll see some of these topics in the second half of today's talk. And our book concludes with a personal view of contemporary topics in combinatorics by the distinguished combinatorialist Peter Cameron, whom many of you will know because he gave the joint London Mathematical Society Gresham lecture last May. So our journey starts in China with the well-known I Ching, the Book of Change. Each of its chapters is symbolized by a hexagram. You can see them here, formed by 6 horizontal lines, either solid, which is yang, or dashed, which is yin. So with 6 lines, and with 2 choices for each line, yin or yang, the total number of hexagrams, and therefore chapters, is 2 to the power 6, which is 64. These are ordered selections with repetition. The order of the lines in each hexagram matters, and yins and yangs can appear more than once in each hexagram. But you notice in this particular arrangement, you notice the arrangement of hexagrams here, each one appears next to its yin-yang complement. So if you look at the any pair next to each other and replace the dotted one by a solid one and vice versa, you'll get the next one. Contrasting with these are ordered selections without repetition, called permutations. Here's a statue of the four-handed Indian god Vishnu holding a discus, a conch, lotus, and mace. How many arrangements are there? Well, the first hand can hold any of the 4 objects, his second can hold any of the remaining 3, and so on. So the total number of possible permutations is 4 times 3 times 2 times 1, which is 24, or what we call 4 factorial. And there's a similar ancient problem, going back to Brahmagupta around 600, concerning the 10-handed god Sambhu. He asked, how many are the variations of form of this god by the exchange of his 10 attributes held in his 10 hands? The rope, the elephant's hook, the serpent, the tabor, the skull, the trident, the bedstead of all things, the dagger, the arrow, and the bow. Unfortunately, I don't have a picture of this, but the answer is 10 factorial, 10 times 9 down to times 3 times 2 times 1, over 3 million different ways. A musical example was given by the French Mennonite friar Marin Mersenne he flourished around the year 1600. In his Harmonicorum Libri, the book of harmonic principles, actually in 1636, he displayed, as you can see here, all the 4 factorial equals 24 permutations of 4 musical notes. Not content with that, he then proceeded to write out in full all the 6 factorial equals 720 possible songs with 6 notes. And they all appear in this book. Yet another example is a medieval commentary on a sacred Jewish text, the Sefer Yetsirah, Book of Creation. No one really knows when it was compiled. The dates 2nd to 8th century don't seem very accurate, but that's all we know. And we'll meet it again later. But this diagram here shows the 5 factorial 120 permutations of 5 Hebrew symbols. Throughout the centuries, many writers have been interested in the combinatorics of poetic meter. Such concerns certainly featured in ancient India. And much later, in 1617, Ericius Putianus, who was a Flemish professor, took a famous 8-word Latin hexameter line in praise of the Virgin Mary. Tot tibi sunt dotes Virgo, quod sidera celo. Thou hast as many virtues, O Virgin, as there are stars in heaven. He then proceeded to try and permute all of these. Well, there are actually in total 8 factorial, which is 40,320 permutations of these 8 words. But each permutation that he chose was required to fit the basic hexameter pattern you can see at the bottom: dactyl, spondy, 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 dactyl, spondy, or if you prefer, dum diddy dum 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 diddy dum dum. So, for example, the main one is tot tibi sunt dotes Virgo quod sidera celo. And you can go through all of these if you like, ending up with sunt celo tot Virgo tibi quod sidera dotes, and so on. Putianus then wrote out as many as 1,022 of these rhythmic permutations, apparently choosing this number because there were 1,022 visible stars in Ptolemy's star catalogue. In the early part of the last millennium, a number of writers started to formulate specific rules for the number of permutations. Here's an example from 1321 by Levi ben Gerson, a Jewish scholar who lived in the south of France and who is credited with introducing the idea of mathematical induction. At the time, there was, of course, no algebraic notation, so he had to present his rules in words. So here is one of the simpler ones. If the number of permutations of a given number of different elements is equal to a given number, then the number of permutations of a set of different elements containing one more number equals the product of the former number of permutations and the given next number. So as I say, this is one of his simpler results. It asserts that n plus 1 factorial is got by taking n plus 1 and multiplying by n factorial, or the way he describes it, n factorial times n plus 1. A different type of combinatorial problem involves combinations. Like permutations, these selections do not allow repetition, but now the objects can appear in any order. And an early example dates back to the 6th century BC, when a celebrated Sanskrit medical treatise of Susruta noted that medicines can be sweet, sour, salty, pungent, bitter, or astringent. And then he proceeded to list all the combinations of these when taken one at a time, two at a time, 3 at a time, the 20 seems to have slipped, 4, 5, or 6 at a time. So the number of these are shown here. For example, if you take 1 at a time, of course, there are 6 of them. If you take 2 of them, you've got sweet, sour, sweet, salty, sweet, pungent, and so on. And there are 15. Take 3 at a time, you get 20. Taking 4 at a time, of course, you realize that if you choose 4 out of them, it's the same as choosing 2 not to include. So the number will be the same as the 15. And then 5 at a time is the same as choosing which one to leave out. And then 6 at a time is there's just one way of doing that. Many early problems on combinations originated in India. For example, around 300 BC, the Jainas studied various combinations of 5 senses, and also studies involving combinations of men, women, and eunuchs, giving rise, no doubt, to a eunuch solution. But as the numbers became larger, it was no longer possible to list every combination explicitly, and more general methods were sought. For example, in a voluminous 6th century work, Varahamihira discovered a way of counting the number of ways of selecting 4 out of a collection of 16 ingredients. And here's his table of numbers, and the important number is on the right at the top. The correct number is 1820. Clearly, he didn't list them all. He must have had some method for calculating it, but we don't know what it was. Many early combinatorial examples arose from religious concerns. The Sefer Yetsirah, which we saw before, the book of creation, asserted that God had created the world and named everything in it, using just the 22 letters of the Hebrew alphabet, which you can see here. God drew them, combined them, weighed them, interchanged them, and through them produced the whole creation and everything that is destined to be created. But how many things can be named with, for example, just 2 letters? Well, according to the unknown author, God combined the Aleph, that's the first letter, with all the other letters in succession, and all the other letters again with Aleph. So he had both orderings. He then repeated this with the second letter, Bet, and so on. And so the total number of pairs is then 22 times 21. And so, because the ordering doesn't matter, we need just half of this number, which is 231. And that calculation and many others appeared in the work. The author then went on to count permutations of letters going up to 11 factorial. Since the longest Hebrew word in the Bible contained just 11 different Hebrew letters. Also, in a religious context, the Catalan mystic Ramon Llull, or Llull, asserted that all knowledge can be discovered by combining the attributes of God in all possible ways. On the left, we see 9 of these divine attributes. At the top is bonitas, goodness. You can also see potestas, power, sapientia, wisdom, and so on. And on the right is the bipartite graph he presented, linking all of these attributes in pairs. And he even introduced movable concentric wheels, which you can see in the book, labeled with these attributes, enabling us to compare them more easily. So you revolve them to give all the permutations, so all the combinations of 3 of the attributes. As we'll see later, Llull's influence over later centuries was profound, with such followers as Marin Mersenne, whom we met earlier, Athanasius Kircher, and even Gottfried Wilhelm Leibniz in his younger years. Different authors have always liked to express their formulas in different ways, depending on the purpose. And in 1658, the Dutch mathematician Frans van Schooten listed the combinations of the letters A, B, C, D like this, starting off with A, and then in the next line he had added B, then he added C, and then he added D. So he added 1 new letter in each row to give you all the combinations. He then observed that if you replace these letters A, B, C, D by 2, 3, 5, and 7, then you obtain the divisors of the number 210. As with permutations, the early part of the last millennium saw formulas for the number of combinations of objects selected from a given set. Such a formula appeared in Bhaskara II's 12th century work Lilavati, rewritten here in modern notation. Supposing you now want to display numbers of combinations, we usually use a pattern called the arithmetical triangle, usually referred to as Pascal's triangle. In this pattern, the rows count the combinations of objects. For example, the row beginning 1, 6, 15 counts Susruta's combinations of 6 tastes that we saw earlier. 1, 6, 15, 20, 15, 6, 1. You notice that each number in the pattern, other than ones, is the sum of the two numbers above it. For example, one of those 15s, either of them is the sum of the 5 and 10 above it, and the 20 is the sum of 10 and 10. And so the triangle can easily be extended as far as one wishes. And in fact, you get all sorts of interesting patterns of numbers here. If you go down the diagonal, the first diagonal on the left is a sequence of ones. The next one is 1, 2, 3, 4, 5, 6, 7, quite a well-known sequence. The next one is 1, 3, 6, 10, 15, 21. These are so-called triangular numbers. These are the number of numbers that you can put in a triangular array of dots. The next ones are the tetrahedral numbers, and so on. And there are all sorts of different results you can actually get from this triangle. For example, if you add up the numbers in any row, you get 1, 2, 4, 8, 16, and so on. You get the powers of 2. And by taking slanting diagonal lines, you can actually also find Fibonacci numbers and all sorts of other things in here. But the arithmetical triangle does more than this. It gives the coefficients arising from the binomial theorem. For example, if you want to multiply out 1 plus x all to the power 3, it's 1 plus 3x plus 3x squared plus 1x cubed. The coefficients 1, 3, 3, 1 appear in the row of the triangle. So if you wanted to know 1 plus x to the fourth, the coefficients are just the 1, 4, 6, 4, 1 that you can see there, and so on. But the so-called Pascal triangle predated Blaise Pascal by many centuries. And the oldest arithmetical triangles we know about come from the Islamic world. So here are a couple. On the left is the earliest known example of a Pascal triangle, or an arithmetical triangle, due to Al-Karaji from around the year 1007. Well, on the right, you can see a slightly later one from about 1200 by Ibn Munim. This one is actually easier for us to read because the numerals that appear there are closer to the Hindu-Arabic numerals that we use today. But you notice that these two triangles the numbers are in different orientations. You need to turn one round and turn it over, turn it round through 90 degrees, turn it over to get the other one. And there are several more Arabic and Islamic examples of arithmetical triangles. I've just got 2 here. A much better known one is the Chinese one, dating from 1303, from Zhu Shijie's Jade Mirror of 4 Elements. Interestingly, it contains an error in the penultimate row. There are 2 numbers in the middle, and they should be the same, and they're not quite the same. I think one of them is a 34, which should be a 35, in case you hadn't spotted it. By the 16th century, these 2 strands, binomial coefficients and numbers of combinations, had come together, and shortly afterwards, several arithmetical triangles appeared. Here's one by Cardano, the gambler and writer on probability from experience. and the writer on cubic equations. This dates from 1570. More attractive, I think, is a slightly earlier one by his rival in the struggle to solve cubic equations, Niccolò Tartaglia. This arithmetical triangle comes from 1556. All you need to do is put ones down the left and right, and you get the pattern that we had before. A truly impressive arithmetical triangle appeared in Marin Mersenne's music book that we saw earlier. He was concerned with the number of combinations of musical notes, and Mersenne extended the table down to selecting 12 notes out of 36. If you're selecting 12 notes out of 36, how many ways are there of doing it? The answer is given in the bottom right-hand corner. There are over 1 billion of them. And he calculated all of these binomial coefficients by hand and put them there in his music book. While he was at it, he also calculated every factorial number up to 64 factorial, which is a 90-digit number. And in his book, and I've looked at his book, you see this whole page of these numbers getting longer and longer and longer. Unfortunately, he made a mistake around 20, and and many of the later values were incorrect, which is rather sad. So why Pascal's triangle? What did his triangle look like? Not perhaps what you might expect. So Pascal's version is shown here. It appeared in a posthumous work. Well, he wrote it in 1654, but it wasn't published until after his death, published in 1665, his work on the arithmetical triangle. Pascal gave the first modern treatment of combinatorics, or of combinations, let's put it that way, clearly describing with proofs the various ways in which the triangle can arise. It can arise out of these results that each number is the sum of the two above it, and other numerical results called figurate results. It arises from the binomial coefficients, it arises from the binomial theorem, and he got the link between all of them, putting it all on a proper theoretical basis. Why is it called Pascal? It was probably de Montmort who named the triangle after Pascal in his essay analysing games of chance, which we'll see again shortly. Well, just as Pascal gave the first modern discussion of the arithmetical triangle, so also the word combinatorial seems to date from this period. We don't really know, but certainly in 1666, the 20-year-old Leibniz wrote his dissertation on the combinatorial art, mainly about permutations and combinations, and greatly influenced by the teachings of Llull, whereby you can find out all facts just by taking basic results and combining them in all possible ways. It was a somewhat insubstantial work, even though its title page, and you can probably see this about halfway down, its title page promised to demonstrate the existence of God with complete mathematical certainty. So combinatorics is indeed a very powerful subject. More attractive than this is the title page of Athanasius Kircher's Ars Magna Sciendi, the great art of knowledge. And you can see the title at the top, and just under it, it says the subtitle Sive Combinatoria, meaning or combinatorics, or if you like, the combinatorial art. Strongly influenced by Llull, it featured much of religious significance. For example, here at the top you can see the eye of God, and then in the middle you can see a displayed list of divine attributes. This book was heavily based on Mersenne's writings. Quite a lot of it was lifted from Mersenne, but put in a more religious context by Kircher. And many of his combinatorial problems were stated in a religious context. For example, he took the word ora, prayer, O-R-A, and explicitly wrote down the 6 ways of rearranging those letters. And then he went on to Amen, explicitly listing the 24 ways of arranging those. Went on to parterre and so on. Returning to Pascal's treatise, it also included an analysis of dice games, which was a popular topic of the time. You can think of the theory of probability arising from that time with Cardano and various other people. Here we can see all the unordered patterns of 3 dice from a 13th century manuscript strangely called De Vetula, on the old woman. But here you can see that the patterns, and then Pierre de Montmort, whom I mentioned earlier, in his 1708 essay analysing games of chance, continued this theme and included this splendid illustration of a card game. So I said he was the one, remember, who named the arithmetical triangle after Pascal. And such discussions of dice games also appeared in Abraham de Moivre's 1718 Doctrine of Chances, a method of calculating the probability of events in play. De Moivre's book, incidentally, presented a discussion of a problem in combinatorics called the derangement problem. If you take 6 letters of the alphabet, A to F, what is the probability that, if you permute them, that none of them ends in its original position? Or if you like, the probability that A, B, C, D, E, F shall all be displaced is, and then you start off with 1, and then you subtract something, and you add something, and you subtract something. This problem is frequently couched in more popular terms. If 6 letters, meaning letters you write, are randomly placed in 6 addressed envelopes, what's the probability that no letter ends up in its correct envelope? So to solve this, de Moivre introduced the so-called method of inclusion-exclusion, which is the pluses and minuses here, and he obtained the answer 265 over 720. This number is actually remarkably close to 1 over e, where e is the exponential number. Indeed, it turns out the number of derangements of n symbols, that's the number of permutations of n symbols in which no symbol is left fixed, is always the integer closest to n factorial divided by e. For example, for n equals 6, the correct answer is 265, whereas 6 factorial over e is about 264.8. It's always the integer closest to n factorial over e. Probability was indeed a thriving preoccupation at the time, and in this posthumous work, Ars Conjectandi, The Art of Conjecturing, published 300 years ago this year, and celebrated by a wonderful British Society of the History of Mathematics meeting last April, Jacob Bernoulli presented his celebrated law of large numbers. This work also introduced the so-called Bernoulli numbers of number theory, although the first 11 Bernoulli numbers had actually been studied a whole century earlier by someone called Johann Faulhaber. If you add together the first n natural numbers, 1 plus 2 plus 3 and so on up to n, you get the result in the first row, a half n squared plus a half n. Bernoulli used a sort of integral sign where we would use a summation or a summing notation. If you add the first n cubes, n squares, then you get a third n cubed plus a half n squared plus a sixth n. Similar with summing cubes, fourth powers, and so on. And this page goes right down to 10th powers. And the coefficients of n that appear on the very right, you can see a half n, a sixth n, minus a 30th n, 1 over 42 n, and so on. These coefficients are the Bernoulli numbers. Although Bernoulli also made mistakes, because in the penultimate line, the minus 1 over 12 should be minus 3 over 20. So that finishes the first half of the talk, which is about permutations and combinations and early combinatorics. And I now want to move to part 2 of the talk, where I'm going to present a small selection of topics from more modern combinatorics. Some of the topics that appeared in the book, or appear in the book, I haven't included today. I will be including them in other talks. You will notice from the sheet, the handout of talks that have been given. I'm giving 2 more talks on the history of combinatorics later this year. In Reading, I'm talking to combinatorialists, and I'm going to be talking about the combinatorial legacy of Leonhard Euler and some of the combinatorial things that he led to. And then on the 7th of December in Birmingham, the British Society for History of Mathematics has its Christmas meeting, and I'm giving my presidential address, where the title is somewhat similar to today's, and there will be a certain amount of overlap, but it's going to be based on a gentleman called Percy McMahon, and there will be various topics like partitions and so on, which I won't be doing today. So let's move on now to Part 2, where I'm going to present this selection of topics from modern combinatorics, several of which were initiated or greatly developed by the 18th century mathematician Leonhard Euler. Perhaps Euler's best known combinatorial achievement was to solve the Königsberg bridges problem, which I'm sure that many of you are familiar with. Here you can see the medieval city of Königsberg, shown here. It consisted of 4 land areas, one of which in the middle is an island, and these parts of the city are linked by 7 bridges. And the problem that the citizens of Königsberg apparently set themselves was to find a walk that crosses each bridge exactly once. Don't repeat anything. You go over each bridge exactly once, and if possible, you return to your starting point. Can this be done? They found when they were trying to do so that they couldn't, but no one had ever proved that it was impossible. So Euler's first innovation was to realize that this is a topological problem. In other words, it's a geometrical problem that doesn't involve metrical ideas such as distance and angle. And he drew this map here, which is much simplified, but includes all the main features of the problem. So you can now try on this diagram to cross each of the 7 bridges exactly once, and if possible, to return to your starting point. Well, you'll find if you try it, you can't do it. So you might want to make the problem easier by dropping the condition that you return to your starting point. Can you cross each of the 7 bridges exactly once? Well, you've dropped the condition, so the problem is easier. It's still impossible, but it's easier. But the question is, given any such arrangement, and Euler looked at other arrangements of land areas and bridges, when can you do it and when can't you? And he, after some discussion, in his paper of 1736, he realized that the answer depends on whether the numbers of bridges emerging from the land areas are even or odd. Basically, it's relevant because if they're all even, then whenever you come into an area, then you can go out again. Okay, and so he stated that if the number of bridges is even for all areas, then the journey is possible, starting from any area you wish and ending in the same place. If the number of bridges is odd for exactly 2 areas, then the journey is possible as long as you start in one area and end in the other. In the middle of your walk, everything is even, so whenever you come in, you can go out again, but then you end up at the other odd area. However, if the number of bridges is odd for more than 2 areas, then such a journey is impossible. So in particular, the Königsberg problem has no solution, because here, if you count the number of bridges around each area, for A it's 5, for B, C, and D it's 3. They're all odd numbers, and therefore you can't do it. Note particularly that Euler did not draw the graph diagram with 4 vertices and 7 edges that we usually use these days to solve the bridges problem. Such a picture to solve the Königsberg problem did not appear until 150 years later. Euler did not draw the graph. He's often credited with inventing graph theory, but he never actually drew a graph. A problem that only gradually emerged as related to this one was that of drawing a given diagram without lifting one's pen from the paper or repeating any line. I'm sure that you've all done this when you were children, trying to draw various pictures. Here's one for you to try. This complicated diagram of Johann Benedict Listing in 1847 can be so drawn because if you look at each meeting point of lines, you get an even number of lines appearing everywhere, except at the two ends. On the left hand, you see 5 lines emerging. On the right hand, you see 5 lines coming in, and everywhere else is even. So you can draw this in one single stroke without repeating any line, as long as you start at the left and end at the right, or vice versa. Incidentally, Listing was the first person to coin the word topology in his book of 1847, Göttinger Studien, and slightly earlier in an 1838 letter he wrote to his schoolteacher. The word topology appeared for the first time. And Listing was also the first to invent the Möbius strip about 6 months before Möbius did. Another type of root tracing problem was the Icosian game, devised by the Irish mathematician William Rowan Hamilton in connection with his invention of quaternions, which I won't go into today. Here, the aim is to visit all 20 vertices of a dodecahedron exactly once and return to our starting point. So here, we're not going over every line. This time, we're actually visiting each point. And the simplest solution you can see here is you start in the middle, B, C, if you go around that central pentagon, and if you visit all the places in alphabetical order, then you can trace out a solution. The vertices were meant to represent, there are 20 consonants in the alphabet, and so the letters are the 20 consonants, and they're meant to represent places, such as B for Brussels, C for Canton, up to Z for Zanzibar. And a solution of the problem corresponded to a voyage around the world. And Hamilton decided to market this. He contacted a games manufacturer, John Jakeson's son, listed at the bottom, which still exists, and sold the game to them for £25, which was a wise move because it didn't sell. But Hamilton also wrote out instructions for the Icosian game. He gave successions of 5 letters, like B, C, P, N, Q, or something like that, and said, how many ways can you complete this particular succession of 5 letters to give you a solution? Yet another recreation was the knight's tour problem on a chessboard, in which a knight follows a succession of knight's moves in such a way as to visit every square of the chessboard and return to its starting point, as shown here. This problem was many centuries old, but Euler was the first to analyze it mathematically in 1759. Incidentally, this particular knight's tour is very interesting because if you number the squares, you can see the knight is on a square numbered on the right. You can see 1, and it then moves down to square 2. If you number the squares 1, 2, 3 up as you go up to 64, then this particular pattern of numbers has the property that if you add any row, that every row and column has the same sum of 260. Sadly, the diagonals don't work, so it's a semi-magic square. And I'm going to return to magic squares later. It was only just a few years ago, I think about less than 10 years ago, that it was finally proved that you couldn't have a knight's tour where you actually have a proper magic square with the rows and columns working and the 2 diagonals. But that was only discovered recently. Euler was also responsible for introducing the polyhedron formula in a letter to Christian Goldbach in 1750. If you've got a polyhedron such as a cube, this has F faces, V vertices or corners, and E edges, then F plus V equals E plus 2. For example, a cube has 6 faces, 8 vertices and 12 edges, and 6 plus 8 equals 12 plus 2. So here is the part of the letter in 1750 from Euler to Goldbach, and this is the first appearance of the formula. You can see it in the penultimate line. H plus S equals A plus 2, H is hedrai, which is faces, S is solid angles with vertices, and A is achies, which is edges. Surprisingly, the idea of an edge of a polyhedron was actually introduced by Euler. You'd think that it went back a lot further to the ancient Greeks or to Kepler, who studied polyhedra, but no, it was Euler that introduced the idea of an edge. And so, although this is sometimes attributed to Descartes, who obtained a result which can be seen with hindsight to be equivalent to this, it was really Euler who was responsible for this formula. If you want to know more about this topic, you should come to Raymond Flood's Gresham lecture on topology in the Museum of London on the 21st of January. To change topic now, a counting problem from the 1850s involved trees and chemical molecules. The theory of chemical valency had just emerged, and the question arose as to how many different molecules you can have with a given fixed chemical formula, such as, for example, C4H10 for the 2 hydrocarbons shown at the bottom of the frame, with 4 carbon atoms and 10 hydrogen ones. Such molecules take the form of trees. Trees are diagrams with no cycles in them, a bit like family trees as long as there's no incest, such as these trees here with 6 vertices. Successful attempts to count trees and molecules were made by the English mathematician Arthur Cayley in the 1850s and 60s, and also by his friend James Joseph Sylvester. Here you can see some pictures of some of Sylvester's chemical diagrams. In an 1878 article based on his inaugural lecture as the first professor of mathematics at the newly founded Johns Hopkins University in Baltimore in America. And it was in this year, 1878, that Sylvester first introduced the word graph in the context of what we now call graph theory. A completely different type of combinatorial problem, also from the mid-19th century, concerns block designs, systematic arrangements of objects into blocks of the same size, with later applications to agricultural experiments and the planting of fields with several types of grain to be compared. The original problem I'm going to mention is the recreational one devised by the Lancashire clergyman Thomas Kirkman, and it appeared in his the 1850 issue of the Ladies and Gentlemen's Diary, designed, it's rather small, you can't see it, but basically for students in mathematics and all persons engaged in that delightful pursuit. What was Kirkman's problem? It came to be known as the schoolgirl's problem, and it was this. 15 young ladies in a school walk out 3 abreast for 7 days in succession. It is required to arrange them daily so that no 2 shall walk twice abreast. When I was professor of geometry here, I gave a talk which I called Problems with Schoolgirls, and heaven knows how many strange websites I ended up on. Anyway, you can see a solution here. It was presented the following year. For example, on Monday, young ladies 1, 2, and 3 walk together, so to 4, 5, 6, 7, 8, 9, and so on. And then you can see the arrangement for Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And the point is that if you select any 2 of the schoolgirls, say 6 and 11, or anyone that you choose, they appear together just once. 6 and 11, for example, appear together on Friday. But that works for any pair that you choose. I'm now going to change tack completely, and we're going to look at magic squares and Latin squares. Magic squares go back a very long way. A very ancient problem, a Chinese problem, involves them. And according to legend, Emperor Yu was standing on the banks of the river Lo, a tributary of the Yellow River, when a sacred turtle emerged from the river, surprisingly with the numbers 1 to 9 on its back, in this arrangement of numbers. This square arrangement, called the Lo Shu, has the magic property that the sum of the numbers in any row, any column, or either of the 2 main diagonals is the same, it's 15. Okay, so for example, you can see in the middle row is 3, 5, 8, or in the top left to bottom right diagonal, you've got 4, 5, 6, and so on, and any of these, they add up to 15. Over the centuries, this particular arrangement came to acquire great religious and mystic significance, and many complicated magic squares were constructed. Later Chinese mathematicians got very interested in these problems, and they created a variety of interesting magic squares. Here's just one on the right. It's an example by Yang Hui, who published the Chinese arithmetical triangle that you saw earlier. His magic square of size 9, with all the numbers from 1 to 81, actually splits up into 9 smaller squares of size 3, each of which is itself a magic square. So he constructed this, and he also constructed various other ones. He constructed a magic square with a 3 by 3 one in the middle, and then he put a ring of other numbers which made it a 5 by 5 one, and a 7 by 7 one, and a 9 by 9 one. And that was another of the ones he constructed. Magic squares actually crop up all over the place. Here's an Arabic one of size 6, found in Xi'an in modern China. And I'm sure that many of you know the well-known 4 by 4 magic square that appears in Albrecht Dürer's engraving Melancholia. Leonhard Euler was also interested in magic squares, and he showed how to construct them from Latin squares. A Latin square is a square array of symbols arranged so that every symbol appears just once in each row and each column. So here are Latin squares of size 3, 4, and 5 from various sources. The 4 by 4 one appears in Llull, and the 5 by 5 is obviously an Arabic one. More complicated are these 2 Latin squares of size 7. On the left, from an Arabic text by Albuni, there's a 7 by 7 square, and on the right is a window at Gonville and Caius College, Cambridge, commemorating the statistician R.A. Fisher, who was a pioneer in the use of combinatorial designs in agricultural experiments. You are all familiar, of course, with sudoku puzzles, and they concern the completion of a partially filled Latin square of size 9, in which each of the 9 main blocks of size 3 must themselves contain all the numbers from 1 to 9. Such puzzles are said to date from the late 1970s, but sudoku designs were used years earlier in the design of agricultural experiments. And here's an even earlier puzzle, a recreational puzzle in France from the 1890s, in which you're given the pattern on the left, and the challenge is to fill in each of those empty 3 by 3 squares with the numbers 1 to 9 so as to yield a Latin square. Pleasingly, the puzzle was described as a diabolical magic square, even though it's not a magic square, and the solution was given shortly afterwards. You can see it, and the pleasing thing about it is it turns out to be a sudoku design. Related to this, a very important concept both in theory and practice is that of a pair of orthogonal Latin squares. The 17th century challenge, due to Bachet de Mézériac and known as the card problem, asks us to arrange the 16 court cards in a square array so that the 4 suits, diamonds, hearts, spades and clubs, form a Latin square, as also do the 4 values, ace, king, queen, and jack. Such pairs of Latin squares are called orthogonal because each possible pairing of a suit and a value appears just once in the pattern. So if you concentrate on the suits, you'll see it's a Latin square. If you concentrate on the values, it's a Latin square. And as I said, each pairing of a suit and a value appears just once. So they're called orthogonal, and in fact, such a famous design has appeared on the front cover of a Combinatorics text. I hasten to add that R.M. Wilson is a very distinguished combinatorialist who is not me. Well, it was Euler that coined the term Latin square in a 1782 paper written in French instead of his usual Latin. He investigated their properties and presented methods for constructing them. And he also posed his famous 36 officers problem. Arrange 36 officers of 6 different ranks and from 6 different regiments in a square array so that each row and each column includes officers of all 6 ranks and all 6 regiments. So he was thus asking for a pair of 6 by 6 orthogonal Latin squares, with the ranks forming one Latin square and the regiments forming the other. Euler couldn't solve this problem, and he believed it to be impossible. He knew how to construct pairs of orthogonal Latin squares of most sizes, 3, 4, 5, 7, 8, 9, and so on, but he conjectured that they cannot exist for Latin squares of size 6. That's the officer's problem, or indeed of sizes 10, 14, 18, and so on, increasing by 4 each time. So they can always be done except if the size is of the form 4n plus 2. Euler was indeed correct that there is no pair of orthogonal Latin squares of side 6. But this fact was not proved until 1900. But he was spectacularly wrong about the rest. In 1959, these 3 combinatorialists, Bose and Shrikanda from India and Parker from US, later called Euler's spoilers, surprised the world by proving that pairs of orthogonal Latin squares do exist for all of these other sizes, 10, 14, 18, and so on. A result that even made the front page of the New York Times with this picture here. So we'd like to see an example of 10 by 10 orthogonal Latin squares. Well, here is a picture. It's not quite the same as the front cover, but if you want to have your own copy, you just need to buy the book and you'll get one. So the outside colours form one Latin square, and the inside ones do as well. And each pairing of an inside colour and an outside colour appears just once. Before I leave the subject of square patterns, it's a fascinating topic, and some of these square patterns that people come up with, whether they're Latin squares or magic squares, can be truly amazing. So here's one of my favourite examples, designed by none other than Benjamin Franklin. So here you can see a pattern of size 16. It's not actually a magic square, it's a semi-magic square. The numbers in every row and every column, the numbers add up to 2056 in any row, 2056 in any column. But there's more. If you take any half row, the first half or the second half, that adds up to half the sum, 1028. And similarly for any column. But you haven't had anything yet. If you take a bit of cardboard and you cut a 4 by 4 hole in it, and you place it anywhere on this pattern, 16 numbers will show through. And wherever you place it, those 16 numbers will add up to 2056. Moreover, we have some pretty coloured patterns on the right. Choose your favourite colour, say the one in figure 1, the yellow. You look at all the yellow squares in the sort of V-shaped pattern, and you add up the numbers there. They will come up to 2056, whatever colour you choose from any 4 of those diagrams. Quite a remarkable thing. So Benjamin Franklin, I mean, his main claim to fame really must be constructing this wonderful magic squares. I can't think of anything else that he did. Well, I'm coming to the end of my time, so let me make some concluding remarks. For many years, the mathematical world didn't take combinatorial mathematics seriously, but things have changed over just the past few years. Things have certainly changed a lot, for example, since I started involving combinatorics, so I don't claim any credit for that. Combinatorial arguments are now used throughout mathematics. You'll find them in algebra, in topology, and in a wide range of practical applications. While most universities regularly teach combinatorial topics as part of their mathematics and computer science curricula. The growth of the subject was greatly helped by well-known figures such as Paul Erdős, who travelled the world working with people on combinatorial problems of great interest and difficulty. While, for example, in America, recent presidents of the American Mathematical Society have included George Andrews, one of our authors of the Partitions chapter, and also Ron Graham, who wrote our foreword. When the 1998 film Good Will Hunting featured a famous MIT mathematician who had supposedly won a Fields Medal for solving a very difficult combinatorial problem it took him 2 years to solve, it was actually an exercise on trees shown here that I've sometimes set to my graph theory students as a rather simple homework problem. Anyway, many people found the idea of a combinatorialist getting a Fields Medal unbelievable. But 10 years later, life followed art, when Fields Medals were awarded to Tim Gowers, who incidentally also gave one of the Gresham LMS lectures here a few years back, and Richard Borchertz for their work, much of which was in combinatorics. And then just last year, the Abel Prize, which is another equivalent of the Nobel Prize, for a lifetime's contributions in mathematics, was awarded to a combinatorialist, the Hungarian Endre Semeredi. The mathematical world is at last taking note. Finally, I should mention that this hasn't been the first launch of our book. Last month, my co-editor John Watkins and I held another event in Colorado with a magnificent cake, which you can see there, which is delicious, featuring the cover of our book. It was heart-rending just to cut it up. But don't be misled. Much of combinatorics can be extremely difficult. It's certainly not a piece of cake. Thank you very much. May I hand over?